In the last lectures, we have discussed about the VERILOG code for different combinational and sequential circuits. Okay. Now, the question is how to check the functionality of the circuit, whether the code that is written is working properly or not. Okay. So, for that we need a module called a test bench. Okay. So, today we will discuss about the test benches in VERILOG. So, what is test bench? Test bench is also another program. So, this can be written in any language, but normally we will use VERILOG only to write the test bench also. So, this is used for the purpose of verifying the functional correctness of the hardware model as we have coded. So, we have discussed various codes, okay, to check the functional correctness of all the codes that we have written till now or any other code. We have to use a test bench. Okay. Then this is also a VERILOG code, and we have written the VERILOG code for the different combinational sequential circuits. Then what is the difference between this test bench VERILOG code and the VERILOG code written for various combinational and sequential circuits? Okay. So, the main difference is actually normal HDLs are synthesizable in the sense. So, after writing the program, we will check for the syntax or logical errors. Once the syntax or logical errors are corrected, then we will transform this into an optimal circuit design. So, this type of code is called as synthesizable code, whereas the code that is written for this test bench need not be a synthesizable one. So, because test bench is basically used to check or simulate the HDL source code. So, this is the original code that we have written. So, it is the reason why the test bench code need not be synthesizable. Okay. And test bench is a powerful tool for auto generation of test stimulus and test results. Okay. This will be clear in the next slide. So, this is the complete setup of the test bench. Okay. So, this is the design under test. Okay. So, whatever the code that we have written, so you have to test that design, you have to take here. Then you have to apply some stimulus, and then you have to check the outputs. So, these two, stimulus and the checking of the outputs, can be performed by using test bench. Okay. So, this is called source code and this is synthesizable. So, this source code can be either in the form of a gate level modeling, data flow modeling or behavioral modeling, which we have discussed in the earlier lectures. Okay. So, to check this source code, we need to apply some stimulus and then you have to check some outputs. So, the application of the stimulus and checking of this result can be performed by using test bench. Now, what are the various steps involved in the test bench? How to implement the test bench? So, the starting point of this test bench is we have to declare the module. So, this is similar to the source code also. In source code also, so initial step is we have to declare the module. Okay. But the main difference between the module declaration in the conventional source codes and the VERILOG code of the test bench module is, here we will not declare the ports. This is one of the important point. So, in the module declaration of a test bench, simply we have written a module mux underscore test bench. So, we have not declared the inputs and outputs. So, what are the inputs of the multiplexer, what are the outputs, that we have not declared in the module declaration of the test bench. Whereas, in conventional VERILOG codes, so after the module you have to give some name followed by the port declaration. So, which signal will act as input, which signal will act as output, which signal will act as a in out, means dual port. Okay. And here we are going to use registers and wires. Okay. So, in conventional VERILOG codes also we will use registers and wires. Okay. So, here the purpose of the registers and wires are, they are used for the driving and monitoring of the signals. So, driving is basically to apply the stimulus, monitoring is to apply to the displays. Okay. So, as we already discussed that the register data type will hold the value until the new value is assigned to it. This will act as some sort of a register. Okay. This data type can be assigned a value only in the always and initial block. Okay. And this data type is used to apply the stimulus. So, here, so this register data type will be used to apply the stimulus. Okay. On the other hand, wire, the second type of the data type, is nothing but a physical connection, okay, which we have discussed several times in the previous lectures. So, it will hold the value that is driven by the port. Okay. And here this data type cannot be used with initial and always block. This is another important difference between the register and wire. So, register will be normally used with always and initial blocks, whereas wire will not be used with initial and always blocks. And this wire is used to check the output. Okay. So, here register is used to apply the stimulus. So, this test bench basically will perform two basic operations. One is applying the stimulus and checking the outputs. So, to apply the stimulus normally we will use register, to check the output we will use the wire. If I take an example of a 2x1 multiplexer, and here I am calling the inputs as y0, y1, different notations, you can use anything, y0, y1 are the inputs, and there is a select line, and there is output called out. This is 2x1 multiplexer. So, here these inputs will be applied through the stimulus. So, we have to define this y0, y1 as register and also select, because these are the inputs. Output will be declared as a wire. Okay. So, this is the second step. The first step is we have to declare the module, and the second step is you have to define the registers and wires. Normally all the inputs will be declared as a register, output will be declared as a wire. The third step is DUT instantiation. This is an important step. Okay. So, we know that the purpose of test bench is to verify whether the designed DUT is functioning properly or not. Okay. So, we have to instantiate our design onto the test module. Okay. So, this will be clear how this instantiation will be done if I give some example. Okay. The general format of the instantiation is we have to write the device under test module's name and then instant name followed by a dot. Here there is one dot is there. We have to give some signal and then within parenthesis we have to give test module signal. This is device under test signal and this is test module signal. Okay. So, these two can be same or you can give different names also. Okay. If I take say for example of the multiplexer. So, here this multiplexer I am giving the name as the device under test module name is multiplexer, instant name is M1, these are optionals. Then, so we have this select. So, the name that is followed by this dot, this select, this represents the names of the signals inside the multiplexer code. So, this is the name of DUT under signal, and then the name within the parenthesis represents that of the test module signal. Okay. So, you can give both the names same or different also. Okay. So, in order to connect this signal to the output, we will use wire or register, they will connect the test bench to the signal in the parenthesis. Okay. So, in order to connect this signal in the parenthesis, so the parenthesis signal is test module signal whereas this is actual DUT signal. So, this can be connected through the wires or registers. So, this select and this select will be connected through this register select declaration, and this Y0 will be connected through this again register declaration. Y1 is connected through this register declaration, and this out will be connected through this Y declaration. Okay. So, basically we have one is design under test, another is test module. Design under test is having 3 signals. So, this is our design under test, 3 input signals Y0, Y1, Y2, Y0, Y1 select and then one output Y. Okay. So, overall if I want to connect this to the test bench, test bench will be having some 3 signals inputs, 1 output. Okay. So, the name of this one also same as this, you can give Y0, Y1 select, or you can give different name also. Okay. In that case, we have to change this. Okay. So, now how to make this connection between these? By using this register connection. So, if I give the register, if I declare this as a register, this will connect to this. If I connect this as a defined as a register, this will connect to Y1, this will connect to select if I give a register. Similarly, the final output of this test module we are calling as out only, you can give different name also. So, these two can be connected through a wire. Okay. So, this is how this instantiation of the DUT module will be done. This is one of the important step in writing the test bench. Okay. So, if I take the general the summary of the test bench module. Okay. So, this is the summary. So, the module we have to give some name, there is no port declaration and then end module. In between what are the various steps as I have defined? The first step is port declaration, second step is you have to define registers and wires, then we have to instantiate the design module under test, then we have to specify the timings. Okay, this I will explain while explaining you some examples. Okay. Then you have to generate the stimulus using the initial and always statements. By default these waveforms will be appeared on the screen. Okay. If you want the values, numerical values, we can use some display commands. Okay. So, display the output, we can display either in terms of the waveforms or in terms of the values. Okay. If you want the values, then we have to use some commands. By default you will get the waveforms. Okay. So, you see the step by step procedure we have to use to write a test bench. So, with this background I will go to some examples of the test benches. So, I will start with a simple AND gate. So, this AND gate is having 2 inputs A, B and 1 output Y. Okay. This one is the source HDL code and this one is test bench. Both we have written using VERILOG only. Okay. This also we have written using VERILOG, this also we have written using VERILOG. I have already described the differences between these two VERILOG codes. So, this is behavioral model of 2 input AND gate. So, we have defined the output register as Y, input is A and B, then always at A or B. So, whenever A changes or B changes, so we have to begin. So, what is the operation? If A is equal to 1, this is binary value of 1 and B is equal to binary value of 1, then output is equal to 1, else output is equal to 0. This is a simple description of this AND gate. Then AND module. Then what is the corresponding test bench correspond to this AND gate? So, as I have told the first step is the declaration of the module, So, this is the module I have given the name as AND to behavioral TB, but there is no port declaration. Okay. So, the difference between this and this is, here we have port declaration, here we do not have port declaration. Then we have to define registers and wires. As I have told, inputs will be defined by the registers, output by wire. So, the inputs A, B are registers, output is wire is Y. Then the next step is you have to instantiate. So, we are instantiating a 2 input AND gate, this one. So, we are assuming that this is the input of the test, and even test bench also we having saving the inputs, even the test bench also having the same inputs as capital A, capital B and Y. So, in that case dot Y we have to apply to the Y, A to A, B to B. Suppose instead of this, if I use some say P, Q, R, say instead of using A, B, Y, if I use P, Q, R, as I have told here. So, this first name is DUT and the second name is test bench within the parenthesis. So, in that case what you have to do is, you have to change this to the test bench values. Y is R, this is A is P, B is Q. Okay. Or you can use the same symbols also. Okay. Then initial begin. So, initial always will be executed at a time t is equal to 0, the time scale. Okay. So, at t is equal to 0, A is equal to 0, B is equal to 0. So, this represents the delay, as I have discussed in the earlier lectures also. So, a delay of 1 second. After a delay of 1 second, A is equal to 0, B is equal to 1. After another 1 second, A is equal to 1, B is equal to 0. After another 1 second, A is equal to 1, B is equal to 1. Then end and then end module. This is the test bench corresponding to a simple 2 input AND gate. So, if we take the test bench waveforms, by default the waveforms will be displayed on the screen. So, as I have written this test bench such that initially A is equal to B is equal to 0. Initially at t is equal to 0, A is 0, B is 0, obviously output is 0. Okay. And after 1 second, 0 1, 1 0, 1 1 pattern after every 1 second. So, at t is equal to 0, A is equal to 0, B is equal to 0, at t is equal to 1, A is equal to 0, B is equal to 1, t is equal to 2, A is equal to 1, B is equal to 0, t is equal to 3, A is equal to 1, B is equal to 1. Okay. That is, you can see from the waveforms. At t is equal to 1, A is 0 still, B is 1. So, output will be 0 only. Okay. At t is equal to 2, this is second instant, 2 seconds. Okay. A is equal to 1, A is changed to 1 and B is changed to 0, still output will be 0. At the third second, at t is equal to 3 seconds. So, this will also 1, this will also 1. So, the output is also going 1. You can see here there is a transition. Okay. If you want this time scale as nanoseconds or picoseconds, initially you can define that. Okay. So, see about the complete 3 different modules. So, the source code, test bench and then simulation waveforms. So, this will complete the testing of a given design under test. Okay. I will consider some more examples. So, this is another example of 2x1 multiplexer. As I have already explained in the earlier slides, this is a 2x1 multiplexer. Inputs I have labeled as y0, y1. This is up to you. And select line by using select only, output is y. So, this is actually VERILOG module. Okay. So, this module multiplexer select I0, I1 then out. We have declared the ports okay, whereas in test bench we are going to see in the next coming slides. So, we do not have this port declaration. Okay. Then the inputs, outputs we have defined, then output we have defined as register also. So, always at select or I0 or I1. Okay. So, whenever any one of these 3 selects, then the output will change. Okay. Output is equal to select and with I0, select and with I1, because we know that this expression already have given in the previous lectures. So, what is the operation of this? Is select is going to decide the output y. If select is 0, this is output. Output is y0, select is 1, output is y1. So, what is the Boolean expression for this output? Is select bar into y0 plus select into y1. So, this is what we have rearranged here. So, this select bar into I0 y0 plus select into y1. Here of course, instead of y0 y1, I think here the inputs are I0 I1. Okay. So, in the previous example I have written as y0 y1, but here in the program this is written as I0 I1. Okay. So, this is I0 I1, then we have to assign the output as output register, whatever this we have defined, that is output, this itself is the output. So, this is a simple VERILOG code for a 2x1 multiplexer. Okay. Then the next step is what is the corresponding test bench. So, as I have told, here I have defined the time scale as 1 nanosecond or 1 picosecond, then module TB I have given just name as test bench, I have not given any multiplexer, this is up to you. Okay. So, you can give any name. So, then the inputs will be registers I0 I1 select, output will be wire out, then you have to instantiate. So, I am using the same names. So, select and then I0 I1 I1 out. So, then initially when select is equal to 0 at t is equal to 10 nanoseconds. I am making select is equal to 1 and I0 is equal to 0, I1 is equal to 1. So, that means what will be the output? Output will be select is equal to 1 means I1 is selected 1. Okay. Similarly, here what will be the out? Select is equal to 1 means I1, what is the I1 value 1? Here select is equal to 0 means I0, so out is 1. Here select is equal to 1, so I1 will be selected, I1 is 0, so output is 0. So, for every 10 nanoseconds we are going to change the select values and I0 I1, correspondingly the output value will be displayed. So, the third step is if we check this test bench waveforms, you can easily see that the select is initially high and this is I0, this is I0, this is I1, this is out. So, when high I1 is selected, I1 is high, so this one is also high. Okay. After 10 nanoseconds, select is 0, select 0 means I0 will be selected, I0 is also going to go 0, this is I0 is 0, so output is also 0. At 20 nanoseconds, select is 1, so I1 is selected, so I1 is high, so this is also high. At 30 nanoseconds, select becoming 0, 0 means I0 is selected, I0 is 1, so this one will continue. Okay. So, at 40 nanoseconds, select is high, I1 is selected, I1 is 0, so this is going to 0. Okay. This is how we can test the functionality of the circuit. Okay. So, if you consider the another combinational circuit which is a full adder. Okay. So, we know that full adder will be having 3 inputs and 2 outputs. A, B, C, sum and carry. So, here I have written this as gate level. As I have told, you can write this code using any of the 3 levels, either behavioral or gate level or data flow modeling. Okay. So, you can write this code using any of these modelings, either behavioral modeling, data flow modeling or gate level modeling. Here I have used gate level modeling. So, module name full adder, then A, B, C sum out. A we have defined as input port and output port, this is as usual, and the wires we have defined as D, E, F. Okay. So, why the wires are required? Because we are going to use this gate level, I should have this circuit diagram of this full adder. Okay. So, this is A, B, C, sum is exclusive OR between A, B and C, and carry is A, B, B, C, C, A, and then finally you have to OR. This is carry. So, here we require 3 wires D, E, F. Okay. So, we have defined the wires as D, E, F, exclusive OR will give directly sum, D nothing but A, B output, A, B output is D, B, C output is E, C, A output is F, and finally we have to take the OR operation between this, it will give carry and then module. Next, coming for the test bench, this is test bench correspond to this VERILOG module. Okay. So, as you have told, the inputs will be declared by registers. So, A, B, C are the inputs, sum and carry are the outputs, so wires, and we are instantiating. So, we are giving the same name, we can give different names also, as I have discussed in the earlier example. Then initial begin. So, initially at 10 nanoseconds or 10 seconds, we have given A as, this is binary representation is 0, 0, 0. So, we have given all the 8 combinations. Okay. After 10 seconds, we are going to stop, end module. Okay. So, if you see the simulation waveforms, we can verify that. So, here, so depends upon the A, B, C values, you can find out the sum and carries. Okay. You can easily verify the functionality of this full adder. Okay. So, these are the few examples of the test benches. In today's lecture, we have discussed about only a simple test bench circuits. So, in the coming lectures, we will discuss some more complicated, including the test benches for the sequential circuits and all. Thank you.